Okay, we're just about ready to go, I think. Hello, and welcome to the fifth lecture of Introductory Astronomy. Today we'll be talking about magnitudes and calendars. So if someone says something is bright, what does that mean? Is it really, really bright, or just really bright? Or is it sort of bright? So we'll be quantifying what we mean by bright. Also, calendars, when things happened. So you're probably all wondering when to plant your crops. And here in astronomy, we specialize in that. We will tell you usually when it's best to plant your crops based on when stars are in the sky. But have you ever seen a sky like this? What is going on there? Things seem kind of dizzying. Is this is time just falling into this big sky funnel? How come you don't have that on your sky? Or do you? These pressing questions may be answered today if you can stay up long enough to watch the lecture. All right. So here's the obligatory 2 slides that I'm federally required to show you. This is Introductory Astronomy, PH1600 for people keeping score at home. This is Lecture 5, Magnitudes and Calendars. Next time we will be jumping off the Earth and traveling into the inner solar system and seeing what we find there. This is originating from the beautiful downtown campus of, not really a downtown area, of Michigan Technological University. And I am still Robert Nemiroff. If that changes, I will let you know. If you're taking this class for credit, which some people are, you go to courses.mtu.edu, and you can download lectures at any time, or you can even take the quizzes if you'd like. You never have to come here in person. You never have to tolerate seeing me personally. You can lurk. You can download the lectures online, you can take the quizzes online, and there's no textbook. But I'm happy to say that we do have a studio audience here today. Now, with all this vagary going on, the second obligatory slide, what are we responsible for? These lectures seem kind of informal. Well, you are responsible for the lecture material. So listen to what I mumble, because it may come back to be on a quiz. However, I will... many of the things I'm talking about will be expanded in Wikipedia entries. So every lecture, I will list what Wikipedia entries you would be responsible for. And these may show up on quizzes, midterms, or the final. You're also responsible for the astronomy pictures of the day. And today, we will be going over the previous 7, including today, previous week's APODs. And again, if you're taking this for actual credit, you want to have had the first 2 homeworks done already, and you want to soon be searching online for the 3rd homework quiz. And here's where you go searching for that. If you can't find it, if you're having problems, send email to PH1600 at mtu.edu. So these quizzes are released around 4 or 5 today, and I think they stopped being available on Monday, I think at 5, so for most of a week. A lot of Wikipedia entries today, but I don't think today's lecture is all that sophisticated. We'll be talking about brightnesses as given by magnitude. So you have your apparent magnitude, you got your basic absolute magnitude, you got your diurnal motion, which is mentioned last time. People tend to collect celestial poles, and I will point out 2 of them. We'll talk about the North Star again, something called right ascension and declination, an equinox, which we're going to have one soon, a solstice, which we're not going to have one soon. And what are these seasons we keep hearing about? Well, up here in Michigan, we have strong seasons. And again, I know we're getting lots of cards and letters about planting the crops, so we're going to be reviewing calendar today. A lot to get to, so let's go right to it. What's the difference between apparent magnitude and absolute magnitude? Apparent magnitude is how bright something appears to you. Absolute magnitude is how bright something really is. So our sun, for instance, is a kind of average but kind of faint star. But it appears in our sky to be apparently really, really bright. So the apparent magnitude of the sun is very high. The absolute magnitude, so if you were to take everything in the universe and you were to put it all at the same distance from you, say 10 light years or something called parsecs, 10 parsecs, which we'll define later. Then you can pick and choose what appears bright to you, because if everything is the same distance from you, then apparent magnitude is the same as absolute magnitude. So absolute magnitude really measures how bright something really is. Magnitudes are a bit strange. A lot of information we have that we use in this world comes down from when it was invented. And when things were invented, there was a different understanding of things than as they are today. So as we'll see, everything from, you say, well, we don't use any old information today, right? We're on the web, everything's modern, everything's great, but it's not true. You use a lot of old information, and we don't even know, some of this information is so old, we don't even know where it comes from. So for instance, Monday is Moon Day. So that came from way back. We don't even know the person who sat down. We weren't at the meeting. We don't know who sat around the table and decided that Monday would be named, Moon Day would be named Monday. So that information is lost. Star names come from way back. So a lot of that information is lost. Now, our magnitude system comes from back when we didn't have, well, we sort of had, but currently, physicists and astronomers more commonly use brightnesses as in terms of common energy units like ergs and joules, and how much that comes in a second. So power or luminosity can be in ergs per second, how much you receive. But back hundreds of years ago, more common was just how bright something was in magnitudes. And they went in the opposite direction from our convention now, and a higher magnitude meant dimmer. And so since we hold on to things from the past, since there's so much infrastructure in deleting it and coming up with a better system, or implementing a better system. Oh, another one just came to my mind. Metric system, in my opinion, is better than the English unit system. But it would cost so much to change all the street signs and the textbooks and things like that, that our good old United States of America pretty much sticks with the English system. Whereas the metric system is more intuitive, things are changed only by changing the decimal places, and most of the world uses metric. But no, we don't, because the cost of changing over, to the best of my understanding. So, some websites that started out real early, like Yahoo, used to be the best way to find things. If you wanted to find information, you went to Yahoo, because it was the natural way of cataloging things was to have people do it, and that was Yahoo's strongest strength. So even in the past, 15 years, this is affecting us. But now there are better search engines than the way Yahoo was using back, 15 years ago or 10 years ago, of using people to put in their favorites and creating lists like that. So, but still, Yahoo, although they've adapted their search engine, is still a very popular site. So things from the past keep permeating the present, even if it's not currently the best way of doing things. And we're stuck with magnitudes. People call different stars different magnitudes. So if you have a magnitude 10 star and you have a magnitude 0 star, which would be brighter? It turns out the magnitude 0 star. The scale is actually interesting. In one interesting way, is logarithmic. So our eyes are logarithmic. What does that mean? That means that we don't see things linearly. So that 5 magnitudes actually means a factor of 100 in brightness. So if something, you can have 0 magnitude object and it can have a real brightness. It can be really bright. And that would be 100 times brighter than a magnitude 5 star. So logarithmic. Oh, no easy way to explain that other than it's a condensed scale. So our eyes and our ears can hear things that are really faint. And it's not just like regular units where something that appears to us to be twice as bright is actually many times brighter. And same thing with hearing. So our ability to hear and see very faint things and hear very faint things and also bright things at the same time allows us to appreciate a solar eclipse, the corona and the bright part at the same time. But it is not easily made into simple units. Put it that way. All right, so unfortunately we're into math a little bit. So here's a relative magnitude formula. So magnitudes are a bit important here. So B sub A is a brightness, which is in typical units of, let's say, energy per second, and let's say that B sub A is the apparent brightness of star A, B sub B is the apparent brightness of star B. Then How do you relate those two given their magnitudes? Well, MB is the apparent magnitude of star B, M sub A is the apparent magnitude of star A, and here's the relation that does it. This is 2.512 and change. We just cut it off at 2.512. Approximately a fifth root of 10 for people keeping exact notes. This is magnitude B minus magnitude A, and that is 2.512 raised to that power. And then this whole thing is multiplied by B sub B. So it's not calculus, but it's more basic than you would get on your four-function calculator. So let's go to an example. So again, this is might seem impossible to some people right now, but hopefully it will seem obvious pretty soon. Let's say that star B in our example appears one magnitude fainter than star A. How many times fainter is this? Well, we can take the previous one and divide both sides by B sub B. So B sub B over B sub B is 1, and it would go away. And then you would get the one on the next page, which has B sub A over B sub B is equal to 2.512 to the M sub A over M sub B minus M sub B. M sub B minus M sub A. It's backwards because, again, higher magnitude numbers like 10 mean fainter. So then we can put in numbers. We said that it's one magnitude fainter. So M sub B minus M sub A is equal to 1. So this means it's 2.512 raised to the first power. So it's 2.512 times fainter. So if it's one magnitude fainter, it means it's 2.512 times fainter. And sometimes I'll just abbreviate it and say 2.5. Because I could say 2.512 and lots of other numbers, but it would take all lecture long, and the amount of information gained would decrease, and people would get bored around the 10,000th decimal place and leave. And it wouldn't increase your understanding very much. So it's about 2.5 times fainter. So let's do another one. Ooh, isn't that weird? The numbers seem to have changed by going to the next slide. Let's do that again in slow motion. OK. Let's say it's now 5 magnitudes fainter. What does that mean? Well, again, we divide by B sub B by B sub A by B sub B. We get this to raise to this power, M sub B minus M sub A. But now we're told it's 5, not 1. 5 magnitudes fainter. So we get 2.512 to the 5th power. And that turns out to be, by no real coincidence, 100 times fainter. So hopefully this is giving you an idea as to how magnitudes relate to brightnesses. They are in the Wikipedia pages cover these. Let's look at apparent magnitudes. What's the brightest thing around? The brightest thing around is the sun. The sun is so bright it is technically minus 26.8. Really, really bright. Again, don't look at the sun, or that's pretty much it for your eyes. The next brightest thing around is up half the time. The sun is up half the time. Half the time it's down. Also up half the time is the moon. Sometimes up when the sun is, sometimes not. When the moon is full and reflecting sunlight, apparent magnitude is minus 12.6. Okay, in this modern age, there are many satellites orbiting the Earth, and these satellites also reflect sunlight sometimes. And there's one series of satellites called the Iridium satellites. And sometimes when they're relatively close by and they're reflecting a lot of sunlight, you can get a really bright flare that lasts for a few seconds. And has anybody seen an iridium flare? No. OK. Well, if you look at APOD, I don't happen to have one lined up here today, but APOD shows you pictures of iridium flares. Sometimes they're confused with meteors on long exposures. But they can become as bright as minus 9.5, so that's bright. Here's something you're probably familiar with, Venus. Many times, if you look up in the sky, you'll see what seems to be an airplane. Now, here in Houghton, we don't have that many airplanes coming in, but in big cities, many times you see a bright light on the horizon, it's a bright airplane coming in. And the way I can tell is I just stand and I stare at it for, a few seconds, sometimes up to a minute, and I see if it moves with respect to the stars or even like buildings or things or trees. If it moves with respect to trees on the time scale of a minute, then it's an airplane. If it doesn't move, quite possibly it's Venus. Venus can get really, really bright. Let's see. The faintest objects visible during the day with the naked eye is listed as minus 3.9 here. I don't know if I believe that. There might be conditions where you can see brighter than that. So that means that Venus is visible even during the day. Mars. There's this internet rumor that goes around pretty much every year now, sometimes in August, that says that Mars will become as bright as the full moon, appear as bright as the full moon, and become as large as the full moon. And strangely enough, people believe this. I don't know, so they get excited about it. Oh my God. But it's not true. But that doesn't mean that Mars doesn't get bright. Several years ago, it got as bright as it's been for the past 16,000 years. And that brightness is apparent magnitude of minus 2.8. Again, Venus gets brighter. If Mars got as bright as the full moon, it would have been minus 12.6. Mars can't come as close as the moon, though. So Mars reflects roughly about as well as the moon does, but it's much further away, and it's not coming that close. So when we get into, let's see, stars, the brightest star is Sirius. Show a picture of that later. And that gets down to minus 1.5 is the absolute magnitude. Canopus, second brightest star, minus 0.7. What is this zero number we keep hearing? Absolute apparent magnitude of 0 used to be the brightness of Vega. So I think Vega's changed a bit, but the 0 point is still used today. It's strange to have a 0 in physics and astronomy. 0 usually means no flux or no something. So if the brightness is 0 in most of astronomy or physics, that means it just doesn't glow at all. But with apparent magnitudes, no, 0 is just one number on this strange scale. Let's say you live in a city and you go outside. Will you be seeing most stars? And the answer is no. You'll be seeing a uniform sky that's lit up from lights from buildings and stadiums and streetlights bouncing off of thin clouds, bouncing off of aerosols in the air, impurities in the air. And so you're not going to be able to see fainter. The faintest star that you should be able to see is about third magnitude. The naked eye planets are Mercury, Venus, Earth, well, of course, Mars, Jupiter, and Saturn. But it turns out that Uranus does get bright enough to be seen with the unaided eye, just barely, because the unaided eye can just about, in a very dark location, see down to magnitude 6. And it's really a spectacular sky if you're able to go out. And it happens here in Houghton, away from the city lights. Just go 5 minutes in any direction and just look up when there's a really dark sky. Now's a good time of year, and you can just see, thousands of stars. And you can see the band of the Milky Way. It's just really an amazing thing. And the faintest stars you'll be seeing are about magnitude 6. Neptune would not have been visible, so Neptune is 7.7. You need a telescope for that. The brightest quasar couldn't be discovered until modern times with telescopes. That's 12.6. So the faintest object observable in visible light with an 8-meter ground-based telescope just now, I think that's probably on around a day's or in one night's integration, is about magnitude 27. It's getting better, I think, with adaptive optics, which I'll discuss later in the course. And the Hubble Space Telescope, on a good day, might be able to see down, good long integration, can see down to magnitude 30. The faintest stuff. Okay, so here's an image I think we've seen before. This is the Belt of Orion, one of the most famous constellations. There's 3 stars in the Belt of Orion. Here's something you don't usually see. It's a bright comet, Comet Hale-Bopp, I believe. And this here is Sirius, the brightest star in the sky. So Sirius, I don't think, is in the constellation of Orion, but you can usually use it to find it. So this is Betelgeuse. It's a star that's more red. This is the Pleiades. It's a star cluster. The brightest yet known star, I don't know if this has been updated. I think it's called is this one here. So it's not the brightest apparent magnitude. So you look at lots of stars and you figure out which one you find their distances. And for the ones you know the distances of, you can then find out how actually bright they are. And so I think this is called the Pistol Star. I don't know exactly where it is. It was found in an image by the Hubble Space Telescope, probably in a cluster of stars so they know its distance, and it is just tremendously bright. So if this was moved to the distance of the nearest star system, the Centauri, Alpha Centauri system, it would be tremendously bright. Okay, the brightest object yet known, I think I think this is a supernova in the distant universe. This was visible for a time scale of weeks. It just got tremendously bright. Now, it wasn't bright to our eyes. We wouldn't go out and be able to read by it, but it was really, really dim, and then because of the tremendous explosion, it became bright, much brighter than it was. In more recent times, in fact, earlier this year, there was a gamma ray burst that for just a few seconds became so bright that it was briefly visible to the unaided eye. And then it went down to well below magnitude 20. So there's no chance to see it. But it was tremendously bright for a short period of time. Okay, slightly moving over to another topic, rising and setting stars. Stars don't themselves rise or set. They just sort of sit in the sky. And we watch them. And if we had a stable platform that didn't rotate, it would be more boring. But our platform, the Earth, which we're confined to, rotates. As we said last time, it spins, so it makes the sky do one full rotation each day. One way to consider the sky is consider all those stars, instead of them as being stars strewn about the universe, you consider them, this was a popular way to think about it several hundred years ago, as just glued to this big sphere that's far from the Earth. And you can call that sphere the celestial sphere. Today we know that celestial sphere is just a useful construct for trying to understand things. There is no big sphere out there. You can't go to the edge of the sphere and then look out and see what's there. But it's useful to think about things that way. This sphere, then you might think of the Earth here as, that's the Earth sign, as stationary, and you can think of the big sphere as rotating. And the rotational poles would be the north celestial pole and the south celestial pole. They are very close to what's known as the magnetic poles of the Earth today. So if you have a magnetic compass, you can hold it out and it will tell you which way is magnetic north. And that used to be the best way to find north. Now the best way to find north is to take out your GPS system and ask it where north is, and it knows. That's more sophisticated. So there is a star in the north that is near the north celestial pole, and that is the North Star, known as Polaris. It was not always Polaris, and it is not spelled with an A there. Polaris is not the brightest star in the sky. It's actually not that bright. It's second or third magnitude. But it's notable by it not moving. So when you go out at night, stars rise and set, but Polaris doesn't. And the stars around Polaris do circles around Polaris. So the bigger the circles, sometimes they're up all the time because they just do a little circle around Polaris. So you go out and you look and it's doing a little circle around it. Other times the circles are so big, they rise and set. So the sun's circle is so big, it rises and sets. If we were to take the sun and move it to Polaris, well, there'd be problems, but it wouldn't rise or set. But there would be other problems. So here is the, again, another picture like I sort of drew. The center is called the celestial equator, which is the projection of Earth's equator onto this fake celestial sphere. The projection of Earth's north spin pole is the north celestial pole, and the projection of Earth's south spin pole is the south celestial pole. Coming to you from Wikipedia, celestial sphere. Okay, so here's a picture of the sky. This is a fisheye picture taken from the Night Sky Live project, which is available at conchem.net for a while. Sort of still is, long story. But here we see what's up in the sky. This is the plane of the Milky Way galaxy here. This is Polaris, the North Star. There are planets here. Jupiter and Saturn are visible, as pointed by the arrows. The belt of Orion is here. This is Sirius. This is Betelgeuse. So this is more of a real picture of what the night sky looks like, and you can see other constellations in this as well. So what happens is, as the Earth spins, the Polaris stays still, and stars go around here. So these stars, they just go a little circle around there, and they're always above our horizon. But these guys rise and set. Northern Lights. So it's not necessarily the Northern Lights that I'm interested in here. It's how to find the North Star. Let's say you go outside and you say, hey, this North Star thing sounds pretty good. I've always pretended to know about it. I nod when people say Polaris, but I don't really know how to find it. So let's say you really want to know how to find it. Well, most people know how to find the Big Dipper, which is part of an asterism, which is part of the Ursa Major, the Great Bear. So you find the Big Dipper, which is many times above the horizon, usually, especially for northern climates. So when you find the Big Dipper, you find this part of the Big Dipper, the Dipper part. So let's make sure people see the Dipper first. Bing, 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 bing. Oops, missed one of the bings. Bing, and bing. That is the Big Dipper. Now I'm going to clear it so you'll see it again in stars. See it? So you take these guys and you draw a straight line and you look for a bright star about 4 or 5 of these lengths away, maybe about 5. That is the North Star, which is Polaris. Now, the North Star wasn't always Polaris. As the Earth's spin, as it turns out, pole moves, the Earth precesses like a top. A top spins really fast, but if the top isn't perfectly up and down, it will precess around. So you have a top that spins, that's perfectly up and down, it spins like this. But if it's on an angle, then it spins like this, but the precession pole goes around another pole, just like a top. So the Earth is like that. So it spins, and right now its spin pole is toward the North Star, but about 12,000 years ago or so, I think the North Star was much closer to Vega. And I think that's one of the older things in language. There are some constellation names that are derivatives of words that were used by languages we don't even know about anymore. So all we have are some of the syllables from ancient languages that tell us things like Vega and things like that. So when you say that, you might think, oh, it's a modern name, but that's some of the oldest knowledge around. It's not even written knowledge. It predates written history. Okay, so here we're starting to get into these strange circles. So this is Mauna Kea, which is one of the best observing platforms on Earth. One of the reasons for that is that it's so high that it's above much of the atmosphere. Here you see clouds below it. Another reason is because it's relatively dry. And another reason is because the waters of the Pacific around Hawaii don't have lots of cities that light up the night sky, for one thing, and they stabilize the night sky, for another thing. So here is the sky above Hawaii, and why doesn't it look like this when you look at it? Because your eye reintegrates. You're watching a movie that your eye reintegrates just about every 10th of a second. So your brain keeps replacing its image that it sees every 10th of a second. And you see another one, and then you watch that movie, and you say, oh, that's reality. So if things happen much faster in a 10th of a second, you generally can't see it. So when someone shoots a bullet or something like that, that bullet is moving too fast for your eye to see. Now, when you really try, humans, it turns out, can increase the rate for small periods of time, their movie rate. And so they can see things slightly faster if they're really pressed than a tenth of a second, but much faster than that they can't. Slower than that you can't do. So with a camera, though, you can keep the camera lens open for more than a tenth of a second, for more than a second, for more than a minute, for hours. It's not so much fun when it's daytime, because then the sunlight makes the whole CCD or photographic film, fuzz out. But let's say you kept your camera open for a couple hours. Then a star that would appear as a point then moves. Well, the star appears to move as the Earth rotates. So here you see this star move, and this star, and this star. And instead of getting points, the rotation of the Earth blurs them into lines. And that's what we see here. Also, we see that the North Celestial Point is not exactly where Polaris is. Polaris actually does orbit the true North Celestial Point. Here we see the image from the beginning, and we now recognize it as a star trails. But this is not just a couple hours. This is 11-hour star trails. So that's hard to do. It's hard to keep your camera steady. It's hard to find nights, many nights, for instance, around now. They're getting close to 12 hours because we're close to the equinox, but really when the sun is near just having set or just before rising, it's very bright on the horizon. So you have to do it in the dead of winter, preferably from a northern location. This distance here will actually tell you how far north. So if you're at the North Pole, that distance is 90 degrees, and the North Celestial Pole is right above you. So these are really long star trails. Now, if you look, my understanding is that there's no star near there. So I believe this was taken to the South Pole, where there is the star nearest the North Celestial Point, called the North Star, is Polaris, but there is no similar star in the Southern Hemisphere. There's no star near the South Celestial Pole. No southern star. This here, that's a meteor, because that happened really quickly. It doesn't rotate with the sky. Could have been a satellite. Here we see a really cool image that you can see the South Celestial Pole, if I can avoid dropping my pen. The South Celestial Pole is here, and the North Celestial Pole is just below the horizon. So this long image was taken with a really wide-angle lens where almost both poles were visible. So a really cool image. And this looks like something out of a time warp, but this is actually just a long-duration panoramic image. Okay, so the point just above you can be called the zenith. It's the point of the celestial sphere directly above the observer's head. The horizon is another term that it's good to know. That is what you think it is. It is 90 degrees from the zenith in all directions. So if there were no mountains, if the Earth was a perfect sphere with no mountains or valleys, then it would always be 90 degrees. But the actual physical horizon has like classrooms and people and mountains and things in it. So it's not always 90 degrees. But if you go up on a hill, it can actually be less than 90 degrees. So planets, the sun, the moon, all rise and set just like the stars. And that's because the Earth's rotation, as I mentioned last lecture, is faster than their orbits, all determined by how fast the Earth spins. Here we see instead of a star trail, this is the sun trail. And the sun is so bright that you don't see other stars. Cleverly taken by famous astrophotographer David Malin. So I'm going to zip along because we're running out of time. So let's see, back to the celestial equator. It is the circle midway between the north and south celestial poles, and it is a projection of the Earth's equator. On the Earth, we use latitude and longitude. So if you look at your GPS, you can find out your latitude and longitude to very accurate coordinates. On the sky, though, since it changes as the Earth rotates, we can't use latitude and longitude because the Earth rotates, so it's not always the same. So the equivalent of latitude is right ascension, and the equivalent of longitude is declination. And there is a 0 point that people use, just like the international dateline for Earth. The ecliptic is where most of the planets in our solar system orbit in roughly the same plane. And so you can identify that plane on the sky, and that is called the ecliptic, and we'll see some images of that later in this course. Here's another picture of things. Here's right ascension measured along the celestial equator. Declination is like longitude. And the first point of Aries is also the timing, related to the timing of the vernal equinox, gives you the 0 point of this coordinate system on the sky. So if you need to know, let's say you want to find a star. If you gave a latitude and longitude, people would say, oh, that's where a point on the Earth is, but that doesn't correspond to where a star is. If you want to tell somebody where a star is, you need declination and right ascension. Here's the ecliptic. This is where planets orbit pretty much in this band there. Okay, over to seasons. There's a common misconception that the seasons are caused by how close the Earth is to the sun. In this misconception, you have the Earth here, and the Earth orbits in an elliptical orbit the sun, which is drawn to be here. So in this misconception, when the Earth is near the sun, then it's summer. And when the Earth is far from the sun, then it's winter. But that's not true. That does cause a slight effect, but the main reason for seasons is the tilt of the Earth. It turns out that here in the northern hemisphere, the Earth is closest to the sun. The Earth is on an elliptic orbit around the sun. The Earth is closest to the sun in January, which is winter time. And it's furthest from the sun 6 months from then, which is June or July. So it's the tilt of the Earth that causes this. So here we have people here when the Earth is tilted so that the sun is highest in the sky and gives you more sunlight for more part of the day. So when the sun is high in the sky, it can, in the summertime, you notice there's more daylight hours. So those more daylight hours are warming you up. And the height of the sun in the sky is giving you more direct sunlight. So those two things combine to make things hot. And those things are related to the tilt of the Earth, not the closeness of the Earth to the sun. And so the Earth is tilted 23.5 degrees relative to its orbit and the spin of the Earth. Here we see seasons in the northern hemisphere. So here the sun would be high in the sky. This would be summer. Here in the northern hemisphere, the sun would be low in the sky. This would be winter. And this would be between winter and summer, so this would be spring. And guess what this would be? Fall or autumn. So it takes the Earth 1 year to go around the sun, and during the year, the spin of the Earth remains in the same direction, but therefore different hemispheres see different amounts of sunlight. So we're coming up on a key date, and that is an equinox. An equinox is equal day, equal night. You might notice that even today, speaking for the northern hemisphere people, we're getting more sunlight. The days are longer than the nights right now. So today, the sunlight, you're going to have more daylight than nighttime. But that's going to change next week. On September 22nd, they're going to be about the same. It'll be equal day, equal night, which is an equinox. And then after that, bad things happen. Well, not necessarily bad things happen. The night becomes longer than the day. And that will keep going until the next equinox. The 24-hour period of maximum nighttime is called the winter solstice for the northern hemisphere. And that occurs on December 22nd. And the summer solstice, when it's the longest period of daylight and relatively little nighttime, is the summer solstice. Again, northern hemisphere bias here. Here's a cool picture taken. So you can see where the sun sets on 3 different times. This is taken from the northern hemisphere, I think from Greece. So in the summer, here's the sun setting, and that's closest to being highest in the sky. In the equinox is in the middle, and in the winter solstice, the sun doesn't get very high in the sky and happens to rise and set over there, relatively far from where the equator would be. There are certain places on Earth where they build big stone monuments to the sun. One of these is Stonehenge. And if you stand in the right place, you can have the sun rise right over one of the big slabs at just the right day. So people do accumulate there. Now, it used to be illegal to go and hang out at Stonehenge during solstices and equinoxes. But now I think they allow people in, so you can see some of these things. There are modern versions of Stonehenge, some of which are relatively expensive to build, one of which is Manhattan. So Manhattan is lined up, the streets. Several cities are like this. This is one of the bigger ones, sometimes called Manhattanhenge. The streets of New York are lined up in a grid, a very accurately portrayed grid, but they don't, on very specific days, for instance, July 13, I believe, is one of the days, the sun rises right down the avenues of Manhattan. Other than that, it doesn't. So if you look right at sunrise, the sun is right down, and it's sometimes hard to drive. It's either right in your windshield or right in your rear view. There's another day. These don't correspond to the equinoxes because the Manhattan isn't lined up exactly that way. There is a tilt to the grid, but the grid is exact. Here we see at the equinox a picture of the sun rising right between some structures on the horizon. So these things then act like another version of modern Stonehenge. The sun will only rise right there on an equinox. And analemma, those are interesting. So let's say you were to go out every day outside and take a picture of the sun at the exact same time of day, say 6 p.m. or noontime. Then you go out and you take those pictures and you superimpose the front parts so they're all the same, and you digitally add them together. You find the sun is not always in the same place. The sun is highest in the summer and it's lowest in the winter, and it traces out during the year an analemma, sort of a figure eight on the sky. And so many times astrophotographers now challenge themselves to try to go out. Anyone can do this. You don't need really special equipment to go out and create an analemma. You can do analemmas of the moon too. They've been computed for Mars too. Okay, back to something I've been repeating. Even the days of the week are some things you say almost every day are related to astronomical origins. So Sunday, you might realize, is related to the sun. Moon Day is moon, but the rest of them are less obvious. Mars Day, TWIS, I believe, is, sounds like twos is, I forget which language. Could be Greek, but I'm not sure about that. A version of Mars. So when you say Tuesday, you're actually saying Mars Day. Mercury Day, Woden Day, is Wednesday. Thor's Day, which is Thursday, it relates to Jupiter's Day. Frigg is another term for Venus. And Saturn's Day, of course, is Saturday. So we're into calendars now. Again, I'm running late, so I'm going to go pretty quick. 1 year is known as the time for the Earth to go around the sun. It does not correspond to an exactly integer number of days. So although it seems like there's 365 days in a year, there's actually 365.25 and little bits more. So that means that the calendar is going to drift 0.25 days a year, and this can add up, which is why we have leap years. So every 4 years we do a leap year. But even that's not completely exact. So originally, the Roman calendar was a lunar calendar, and it lost many days a year, although it had an occasional leap months. So if you lived thousands of years ago, you wouldn't have this current calendar. No, thousands of years ago, you'd have the Roman calendar, and occasionally the Roman emperor would declare a leap month. How about that? Then the Julian calendar, actually in Roman times, Julius Caesar induced in 46 BC that there's 365 days each year, and there's one leap day every 4 years, and then there was a much better calendar. And this helped people know when to, people like to plant crops based on certain calendar days, like, April 15 or something like that. And if the emperor adds a new month, then that sort of throws off your schedule. So it's good to have a good calendar, so then you know what day to plant your crops. So the Julian calendar was much more accurate and didn't drift as much as other calendars. The Gregorian calendar was decreed by Pope Gregory XIII in 1582, only 500 or 420 years ago or so. And this accounted for the inexactness in the 0.25, which was creeping up. So what this one did is it took away leap days every 100 years or so, except every 400 years. So there were more rules. So leap years were 1600 and 2000, but not leap years were 1700, 1800, 1900, and 2100. So you might know that this year, 2008, was a leap year. That would have been true in the previous calendar, in the Julian calendar, as well as the Gregorian calendar. Nowadays, we know the Earth changes its rotation very slightly due to things like earthquakes. So there are, and weather patterns, big weather patterns. So there are reasons to add fractions or seconds to the calendar. And so many years now, although it's not obvious to most people, there are fractions of seconds or leap seconds added to the, or subtracted, based on how the Earth's rotating, because the Earth doesn't rotate exactly the same speed due to changes in its structure. All right, so this goes back to our original. We're going to do apods after this. This, again, was the original slide and shows that this is really, we're just watching the Earth rotate with a camera with these things. So now I'm going to go to the astronomy pictures of the day. This was something I was going to do. I'm going to go to apod.nasa. Let's see if I can click on it. Okay, so let's go to mountaintop meteors. So for last Thursday, September 11th, there was a picture of a time-lapse picture of meteors coming in. I think this is the Perseid meteor shower that occurred in August. This is taken from one of the highest points in Romania, the Omu summit. 2,507 meters long. So you can see many meteors come in here. I like the perspective of a person in there watching that. It would take probably hours to get all these meteors. One weird thing is these things seem to be coming to a convergence point below the horizon, which just really means that the real convergence point is below the other horizon. And I won't go into that in more detail there right now. Going to the next apod, assuming this computer works. Yay. Okay, there's been a bunch of planets. This one was taken from Perth, Australia. And on September 1st, the moon was visible. The downtown Perth was visible. I believe this is Venus, bright again. Remember we discussed how bright Venus was? Oops, let's clear this. Moon, Venus, Mercury, and Mars. So here you saw 3 planets, all in the sky, in the same location of the sky at the same time. This was early evening in early September. It's visible in the southern hemisphere. Okay, here we see one of the more spectacular galaxies visible in the sky, called the Triangulum Galaxy, also known as M33, the 33 galaxy on Messier's list. So we'll talk about Messier's list. This is a relatively nearby spiral galaxy. I would guess we'll talk about galaxy types later in the course. This is type SC. It's a relatively small SC galaxy that's near the Andromeda Galaxy. Here you see the center of it, and here you see some really spectacular spiral arms. Here you see a dramatically large star-forming region. So this is a really spectacular looking nearby spiral galaxy. Okay, here we have some nebulas in our galaxy. This is the Heart and Soul Nebula. Let's see, I believe this is the heart and this is the soul. They are giant star-forming regions where there are young clusters called open star clusters. You can see some of the bright stars of the open star cluster toward the center of these. And what they are doing is they are, well, a star cluster is forming. So a lot of this dust will be pushed out, evaporated, or pushed away. And in 100,000 years or so, only the bright stars will be easily visible. And you'll have an open star cluster. Okay, this is an odd thing on the sky caught by the Hubble Space Telescope. This is a part of supernova 1006. So in the year 1006, there was one of the most violent explosions that did become bright enough to be seen. Remember, we're talking about this was not only apparent, absolutely bright, but it came apparently bright. It was brighter than Venus in the sky for a while in 1006. And then it faded. And what we see now is a much larger supernova remnant, and part of that remnant is this shock front moving out. And the shock front looks like an unusual ribbon on the sky. So we like the cool and unusual here at APOD, so we highlighted this. So it's taken by the Hubble Space Telescope as part of the Hubble Heritage Project. Here we see I'm hawking my course. This is another picture of the Heart Nebula, but this time it's a zoom in to see a lot of these pillars of star creation on the right here. So these bright stars are part of the open cluster of stars that is forming. There are open cluster stars forming here in the pillars, but many of the bright stars, their winds are pushing out these gases and ionizing, and the denser knots are holding out, and those are the star columns that are forming. And those star columns are being compressed and forming stars themselves. And I really like this image because it's just all these pillars all together. It's like a lot of, I don't know, little birds chirping for food or something. It was a surreal picture. And the last one is today's image, which is 2 huge clusters of galaxies. So now all these points you see, well, except for this one, that's a star. All these other points you see, they're all galaxies. And there are 2 of the largest things known in the universe colliding. 2 whole clusters of galaxies are colliding together. And when they do that, the gas gets hung up. But the dark matter goes right through itself. And so the dark matter, here is in this color, is spread differently than the normal matter. And anything that tells us a clue about dark matter we consider to be interesting, because we don't know what dark matter is. we know that regular matter like us, made of hydrogen, helium, we know relatively a lot about that. But this dark matter appears to be attracted gravitationally to regular matter, appears to attract regular matter gravitationally, but we've never found a piece of it. People are looking for pieces of it, but we know that a lot of it is in galaxies and clusters of galaxies, and here we see an evidence that it doesn't collide with itself. So it's not like normal matter, which collides with itself and creates hot gas. This is the Chandra X-ray telescope image of the hot gas, shown in pink. But through a process called gravitational lensing, we're able to find where the most of the mass is by distortion of background galaxies. And that tells us where the dark matter is. And they're separated from each other. And so that's a really interesting finding. And the system is called MACS J0025, and then that's actually coordinates on the sky in right ascension and declination. Okay, so that's what we have for tomorrow, for today. And next time we will go into the inner part of the solar system. So see you next time.